Swarup has been here for 3 years now almost, and more than 3 years. He came
Just
in 2005. He has a PhD from Purdue University, so he came from Purdue right after graduation. And he has been involved in computer-aided design, nanotechnology, and even implantable microelectronics and also MEMS for quite a while. He has numerous publications. He has been on the program committee of several conferences, and he also has several best paper awards in the field, and he's quite well known. So it's a pleasure to have him give us a talk on implantable electronics and nanotechnology.
Okay, thank you very much, Krish. So I will start with an introduction about my research lab. The name of the lab is Nanoscape. It's targeted to architecture, circuit, and model for nano computing. So it's basically all nano. There's a dedicated website for this lab, and of course the main workforce for this lab is my students, Somnath, Rajat, Sitaram, David, and Kirti, and the research activity is sponsored by DARPA, Air Force Research Lab, Intel, and NSF. Now let's look into the research we do in the lab. There are 3 main topics. The first one is low power and robust system design in nanoscale technology. In low power, in particular, we look into leakage reduction techniques and also thermal management. We also look into variation tolerance. We'll talk about that shortly. And then in variation tolerance, we look into 2 specific type of circuit/architecture design techniques. The first one is called self-calibration and self-healing. It turns out that the integrated circuits can heal themselves if you can design it appropriately. And also we look into robust logic design techniques in nanotechnology. We work on another topic called adaptive nanocomputing. There are recent or emerging devices coming into picture like carbon nanotube, molecular crossbar, single electron transistor, or quantum dot. For these devices, you need a different paradigm for computing. Starting from computing model, going to architecture and circuit design techniques. So we look into circuit architecture and again computing model for these emerging nanoscale devices. And finally, a major thrust of this lab has been developing implantable electronics, in particular electronics for neural interfacing, and this work is being carried out in collaboration with Professor Hillel Chiel in biology, Professor Steve Garbrick, and Professor Masud Tabibajar in ECS. So here is the list of collaborators. It's a long list, and some of them are not here actually, but it pretty much encompasses the major people I am working with in all these three topics. Now let me give you an introduction about nanoelectronics. And it turns out that nanoelectronics has a fascinating journey starting from 1958, when Jack Kilby developed the integrated circuit, when he first integrated a single transistor in a piece of germanium. So that was a breakthrough invention in the history of electronic industry, and that has driven the industry for past 4 decades in a phenomenal rate. And I believe no other industry has made progress in such a rate. Now let's look into the rate of progress. If you plot the computing power for different processors developed by Intel across technology generations, you will see there is a near exponential growth in computing power. Not only in computing power, but also the integration density has increased in an exponential rate following the famous Moore's law. Now the question is, what is the key to this exponential growth in computing power and integration density? The answer is actually very simple. It's technology scaling, which means every generation the transistors, which is the main building block of electronic circuits, has been scaled down aggressively. And by scaling we mean the dimensions of the transistors, the length, width, and gate oxide thickness has been scaled down by about 30% each technology generation, which gives rise to doubling the transistor density, which means in unit area or unit silicon area, you can cram twice as many transistors if you go from one generation to another generation. So not only the length, we are scaling the gate oxide thickness, as you can see here. This is the cross section of a typical nano transistor. Now the oxide thickness scaling actually leads to faster transistor, which means the transistors can now switch at a faster rate. And finally, we are also scaling the supply voltage and transistor threshold voltage, leading to lower active power, which means if you scale the transistors, you actually have lower active power for on switching. Now that's an interesting question, because if you have lower active power, why is power a problem? So we'll look into that shortly, but it turns out that by scaling transistors, not only you have improvement in integration density, you have improvement in transistor switching speed and also in active power for on switching operation. Let us look into the timeline. A very interesting slide we have here, which gives you a synopsis about the progress of electronics from micro to nano, from silicon to non-silicon. Now if you look into here, actually Intel came up with their first processor in about 1971. Right? It was a very in today's standard, it was a toy processor, but that was again a phenomenal discovery in terms of electronic industry. By that, at that time, the transistor dimension was in the range of 5 micron. Now gradually the transistors have been scaled down, and we have moved to silicon microelectronics to silicon nanoelectronics. And by nano, we mean the basic feature size of the transistor has been scaled down below 100 nanometer. The minimum feature size of the transistors, which is indicated by the minimum size you can etch in the process technology, has been scaled down below 100 nanometer, and that has happened somewhere around 2000. So we have moved from micro to nano. Now it turns out that the conventional CMOS technology is expected to run out of gas in just few years. So what next? People are looking into new technology which are non-silicon, for example carbon nanotube, for example molecular crossbar, which is being pioneered by HP. So these technologies have potential to replace CMOS in near future. And interestingly, they have quite different IV plot or IV characteristic compared to traditional transistors. And that means that if you want to design circuit or architecture with those devices, you need to think about a different architecture circuit styles. The conventional styles are not going to work with these new devices. So there are a lot of challenges ahead of us, which means that if you really want to exploit the benefit of nanoelectronics, you need to deal with the problems, and the problems are in terms of power, in terms of variability, and in terms of robustness. So we'll talk about that in more details. So the verdict is the power will continue to increase. So low leakage and leakage tolerance would be a key focus of nanoscale design. Dynamic power management, not only static, not only design time power management, but runtime power management will be key. Process variation, which is variation in device parameters due to process imperfection, would be a significant problem. And to deal with that, not only you need to deal with the manufacturing process, we have to design circuit and architecture in such a manner that they are tolerant to device parameter variations. So the idea is that nanoelectronics has a lot of promise, but significant challenge to face for the design engineers. So this is how the technology has moved in terms of the basic transistors. Currently we are using bulk CMOS, and bulk CMOS is a planar device. We all know that this is a typical cross section of a bulk CMOS, which is comprising of a P channel. Let's say for NMOS transistor it has a P channel and N type source and drain. Now, the bulk CMOS has several variants. For example, you can have SOIs, silicon on insulator, and you can have PD or partially depleted SOI or fully depleted SOI. So, these are devices with single gate. It turns out that if you scale down the technology, then the control of the gate on channel conductance is actually reducing. If you look into a transistor, the basic switching operation happens because you can control the channel conductance by applying a voltage at the gate. But if you scale down, then that control is going down. So, people have thought about replacing one gate structure by multiple gates. So, they have talked about 2 gates, they have talked about 3 gates. For example, Intel is promoting a tri-gate structure where each transistor will have 3 gates, which is wrapped around the channel. AMD and IBM are looking into a structure called FinFET, which has multiple gates. Again, the motivation is to have better control on the channel conductance. So, that effectively gives you less leakage current and better performance. So, these are called multi-gate devices. Now, if you go along, the multi-gate devices will also not be able to be scaled further, and people are predicting that beyond 2015 or so, multi-gate devices, even multi-gate devices will not be able to be scaled, or they will reach the physical limit of scaling, and then we need to look into completely different switching devices built with different materials. For example, nanowire, nanotube based devices. So, that is basically the technology trend, and if you really want to exploit those emerging devices, you need to couple them with new circuit and architecture design techniques. Yes.
Go back to that previous slide. The one thing that always mystifies me when they say like 45 nanometer technology and 10 meter nanotechnology, what do they define? Is that the width of the channel, and then how does that affect when you talk to nanotube? Is that the width of the tube or the length of the tube?
Yeah. In terms of transistor, the feature size is defined by the minimum dimension you can etch, and that is typically the gate length, the physical gate length. So, that means for transistor, it is the physical gate length. Yeah. For nanotube, again, it depends on how the nanotube is used as a switching device. There are different variants. For example, carbon nanotube can be used as a field effect transistor, where the carbon nanotube is used as a channel, and there are different source and drains. So, if this is channel, again the channel length is your minimum dimension, and that can be few nanometers. Okay. So, that is the device trend.
But the width is also comparable.
Yeah.
Carbon. For the nanotube, the width of the wire
No, carbon nanotube is basically a sheet of graphite which is rolled, and
yeah, that's one way to do it.
yeah, that's the common way to do it. Now, so that's one side of the story. But the fact is that even if you scale down the device, you need to actually, depending on application, you need to have different power and performance targets, and that vary along with application. So, this is a plot which shows that different applications will have different power performance requirements, and we can categorize the applications into 3 areas. The implantable devices will fall into ultra low power applications. So, if you look into the hearing aid or cochlear implant or pacemaker, they are ultra low power and very low performance. So, they fall here, low performance and low power. In the mid range, we have the portable electronics, which has moderate performance and moderate power requirement, and in the high end, we have high power requirement by but high performance systems. For example, the desktop, server, network router, such and such. So, the idea is that if you are trying to design a system using nanotechnology, you have to be careful about your design target, and you can exploit the benefit of nanotechnology, but you have to make sure that you meet the power and performance targets for a particular application. Let us look into the challenges. As I mentioned, the main challenge of nanotechnology is power. The power is increasing, and although the switching power is decreasing, the power for switching one transistor is decreasing, the overall power and power density is increasing significantly because you are integrating more and more devices and because you are running them faster. So, the power is increasing due to higher integration density and due to higher operating frequency, even though the power for one switching is reducing. Now, what is the impact in terms of design? In terms of design, the impact is in battery life, in cooling cost, and also power translates to heat, and heat actually causes a reliability problem, right. So, it is a major problem. We are not looking into test challenges, but it turns out that all these problems also have implication in testing. The second major problem is process variation. We will talk about in more details, but process variation contributes to decreasing manufacturing yield. And finally, due to reduced current and voltage level, we have reduced noise immunity, which means the transistors are now more vulnerable to noise, and the operation which is less robust, it is vulnerable to soft errors. Soft errors are caused by high energy alpha and neutron particles, so it is vulnerable to soft error. So, these are three major problems in designing circuit architecture with nanotechnology. So, if you are trying to build a system with nanoscale devices, you have to be careful and you have to address all those challenges. So, let us take a closer look at these problems. So, this is a plot which shows how the power of different Intel processors are increasing over the years. As you can see, the average power for the processors are increasing almost steadily, except some outlier here, almost steadily over the years, and that has a cost in terms of battery life and cooling cost. But a major problem, a more significant problem, is the power density, which is computed as the power dissipated in unit area. And if you plot it, you will see that today the power density of a typical processor is close to the power density of a hot plate. Now, if that trend follows, pretty soon in near future we are going to touch the power density of a nuclear reactor or rocket nozzle. So, that is really alarming. It turns out that the power density across the die is not uniform. The region which has the higher activity will have the high power density. So, if you are trying to design a circuit to reduce the power density, you have to actually give more emphasis on this region, which is typically the integer arithmetic logic unit and integer register file, which has the highest activity, because the power is proportional to activity and temperature or heat is proportional to power. So, in terms of implantable device, power density is a major problem, because if you heat up the surface of the die, that is going to cause tissue damage. So, as a designer of implantable electronics, one needs to be careful about the power density issue, needs to make sure the power density is below a threshold in order to ensure no tissue damage. Now, let us look into where the power is coming from. There are two components of power. One is the switching power or dynamic power, the other is called leakage power. And the leakage, as the name indicates, is the power when the transistors are not doing any useful operation. The dynamic power has two components. One is the switching power of the logic gates, another is the switching power of the clock line. It turns out that clock power is significant component of total power. It is about 40% of the overall power. So, it is a significant component, and one needs to take care of clock power in a conventional VLSI system. Similarly, the leakage has two components. One is the leakage in standby mode, when the system is not doing anything in standby, and another is the active leakage, and this leakage is the leakage of the idle part of the system in active mode, which means even if the system is working, there are certain parts which are not used, and leakage in that part is called active leakage. So, let us give you a brief overview of leakage current. the leakage current is, as I mentioned, is the current in the off state of the transistor. So, even if the transistor is turned off, there is a current flowing, and this current is called leakage current, and depending on the leakage flow mechanism, there are different components of leakage. The most important component is called subthreshold leakage, which flows from the drain to source. And if you plot subthreshold leakage for different technologies, you will see that the leakage current is increasing exponentially, and that is an important trend to note. If it is increasing exponentially, then the leakage current is becoming more and more important in nanoscale devices. And I talked to Intel very recently, and unofficial information from them is that right now for the processors the total leakage power is 50% of the overall power. So, that is a lot, and you cannot probably tolerate that much power, and that is true. Actually, that can be extrapolated from this plot again, which is borrowed from Intel, which you can see that for different technology generation, the leakage power is the contribution of leakage power in overall power is increasing, and in 65 nanometer it was 32%, in 45 it is 54%. It is a predicted trend, but the current technology is actually having 50% of leakage power for the modern processors. So, leakage is a significant problem in nanoscale design. Another problem, as I mentioned, is process variation, and the process variation is caused by variation in different device parameters, for example, the channel length. Now, even though you design a transistor for channel length X, due to manufacturing imperfection or due to less control on the manufacturing process, the channel length cannot be X, it can vary by 10 to 20%. Similarly, the number of dopant atoms inside the channel, that can also vary significantly, and if you look at this plot, you will see that for different technology node, the number of dopant atoms in the channel is decreasing significantly, and if you look into 65 nanometer, it is already less than 100 atoms. Now, if you have so few atoms, just like due to process variation, if your number of atoms change, then you have significant impact in transistor threshold voltage. It turns out that due to random dopant fluctuation, two transistors on the same die, even if they are side by side, they can have different threshold voltage. Now, that is a major problem, because if the transistors have different threshold voltage, then designing memory, designing even logic circuit becomes a major challenge. If you look into memory, that is completely dependent on a perfect match of the transistor strength. Now, if you have variance, then the memory circuit is not going to work. The similar impact can be in analog circuits. So, these phenomena actually are significant in terms of logic and memory design, and for set of Intel processors, they have seen that due to these variations in device parameters, we have a corresponding variation in system parameter, and this is the system leakage and system frequency for processors. You see that for the same process, same design, after manufacturing, we have 30% variation in frequency, and we have 5x variation in leakage current for 130 nanometer technology. If you go to 45 or 65 nanometer, this variation can be more than 100x. This delay is the maximum operating frequency, so the processor frequency. So, that is a major challenge, because that is a major challenge because device parameters are no longer deterministic. So, what you design, you do not get that. That is the problem. So, you have to design in amidst uncertainty. So, that is a major problem. Now, let us look into implantable electronics. And implantable electronics is a system which is implanted inside the body for sensing, typically for sensing bioelectric or biochemical signals. It actuates body parts, it can actuate, sometimes it does not, it just monitors. It is often equipped with telemetry system for wireless monitoring or control. It is mainly used in therapeutic applications. There are different emerging applications. We will talk about that shortly. Three main components of a typical implantable electronic system. The first one is measuring electrodes. The second one is analog electronics for preconditioning of data, particularly converting the analog data to digital or vice versa, and amplifying the signal, and also communicating with the outside world. That is the telemetry system. And the final component is a digital signal processing computation unit, which analyzes the signal and generates appropriate command. So, there can be multitude of different implantable electronics for different diagnostic or control functions. For example, we can have deep brain stimulation, we can have artificial retina, we can have cochlear implant. Actually, that's very that's an well established technology right now, both cochlear implant and deep brain stimulation. We can have defibrillator, pacemaker, identification unit and insulin dispenser. So, there are different types of implantable electronic system which can be used for different purposes. Now, one of the prominent use of implantable electronics is for interfacing with the central nervous system for different purposes, and a major one is deep brain stimulation. As I mentioned, there is a product already available in the market, and this stimulator actually control the tremor. It's a treatment for seizure and epilepsy or Parkinson's disease, which are very severe neurological disorder. We can do neuromuscular stimulation for pain management, bladder control, for treatment of incontinence, and also we can do functional stimulation. People can think about neural prosthetic devices. Actually, there are already products for that, like cochlear implant. Again, visual prosthesis being looked into. There are also efforts to bring products in the market. Brain machine interfaces for closed loop neural prosthesis. This is an emerging area which can be used for artificial limb movement of cursor using brain signals like that. So, these are the pictures for DBS and cochlear implant. From a famous article in 2001, that is by Nicolis. The article is Actions from Thoughts that published in Nature. What he did, he described a typical system for neural interface, and it consists of several components. The first one is called multi-channel acquisition system, where you monitor brain signals using several electrodes or high density electrode array, precondition them using analog electronics and do digital signal processing. From the signal processing, you can do real time analysis of the brain signals and correspondingly and send it out to the outside world using telemetry devices. On the other hand, the telemetry receiver can receive signals from outside, process them and stimulate certain body parts. So, this is a typical system for interfacing with the central nervous system. People are thinking about new applications. Some of them are really crazy. Very recently, there is an application being investigated by several universities, including University of California at Irvine. They got a $4 million grant from US Army, and the idea is to develop a thought helmet, a helmet kind of device which can be used for secure silent communications by the troops. It is not implantable, but one can easily extend the idea to an implantable system, where you do not need to wear a helmet, everything would be inside the brain. So, there are a lot of emerging, you can call it crazy applications which are coming into picture, which can use implantable devices effectively, not for therapeutic use, but for communication. People can think about this is recent research being carried out by several people, including people in our department. In this case, one can think about integrating an implantable device with the parasympathetic chain or peripheral nervous system of the body, and then control different internal organs. So, some initial analysis shows that the signals are are similar to the signal from ganglia or from other parts of the nervous system, and we can actually apply different signal processing to denoise the data and identify units which correspond to muscular dynamics. So, it turns out that one can monitor the pudendal nerve, and based on the signal at the pudendal nerve, the pressure of the bladder can be controlled for treatment of incontinence. So, these are emerging applications of implantable device which can be used for treatment of different disease. So, let us look into the system level view of implantable system. This is this came out with my collaborative work with Professor Hillel Chiel, Professor Garverik and Professor Masoud Tabibazar. So, what we do is we develop an implantable system to monitor the neural signals from the ganglia of a sea slug, and sea slug is an animal, invertebrate animal, which is a very good test bed for studying the hardware and algorithms for neural interfacing. So, if you can put a set of electrodes in the ganglia of aplysia, one can monitor the extracellular signals, and those signals can be analyzed by a signal processing units, and of course, it has to be preconditioned by analog hardware. So, the idea of using this implantable digital signal processing unit is to identify the spikes, and the spikes correspond to neural activity. So, if you can identify the spikes, one can significantly compress the recorded data and transmit it outside to the outside world. At the same time, by identifying spikes, one can also find out typical behavior in an animal. So, we have done some preliminary work using pre-recorded data, and this is the typical system we have used. So, there is a recording electrode coming from the ganglia, preamplifier to amplify the signals, analog to digital converter. So, this is the analog part, analog front end, and then we have signal processing block, then we have the telemetry system. And we also have a control unit which can take information from the signal processing block or from the outside world to stimulate certain nerve cells. So, that is the overall system, and this is a drawing about the resultant system. The drawing was borrowed from Professor Garverik. The target package volume for this device is 0.5 centimeter cube. It is an ongoing work, so it is not done yet. So, we plan to do it in near future. The total power distribution has to be less than 1 milliwatt. The sampling rate is 25 kilohertz, and the sampling resolution is 10-bit precision. So, as I mentioned, there are three major components. The first one is high density electrode array, and we need an electrode array for neural interfacing because many activity of the neurons happen as by a group of cells, not by a single neuron, by a group of cells, and the group can have 100 to 1000 neurons. So, you need to record from multiple neurons at the same time or multiple nerve cells at the same time to understand the activity of the neurons. So, high density electrode array for sensing and actuation is an important requirement for neural interfacing, and nanotechnology can help here, and that has been shown by several researchers. Recently, Professor Jorman and Professor Tabibazar came out with electrode technology, which are definitely superior than the previous ones. I am not going into details about them, but it turns out that one can leverage nanotechnology to develop high density electrode array, which can be flexible or which can have superior properties in terms of conductance and so on. So, that is about high density electrode. In terms of analog electronics also, we can leverage from the nanotechnology, but we have to be careful here because analog circuits typically do not scale as good as digital circuits. The reason is that they are more vulnerable to process variation, they are more vulnerable to leakage current. So, one has to be careful about exploiting the advantages of nanoscale devices in implementing analog electronics. Robustness of operation is a major problem, and the transceiver power, which is the power required by receiving and transmitting data from and to the outside world. So, the transceiver power are major challenges for analog electronics. So, this is already pre-developed analog electronics by Professor Garvik, and it is using a battery which is 3 volt 160 milliampere hour lithium ion battery. The projected lifetime is 23 hours. Definitely it is not good enough. So, we are trying to improve the power dissipation of the entire system, so that we can reduce we can improve the battery life. So, let us look into the digital signal processing in implantable electronics. So, the first thing is, what kind of signal processing we need? Nervous system needs to be monitored and controlled, as I mentioned, at cellular level, and number of cells, nerve cells, needs to be recorded at the same time in parallel. Now, if you record hundreds to thousands of electrodes in parallel, then definitely the transceiver power and the bandwidth requirement becomes a significant issue. And here is an example. If you are recording from 100 electrodes at a rate of 25 kilohertz per channel with 10-bit precision, then the data rate for the raw data rate, if you do not do any onboard compression of the data, the raw data rate is 25 Mbps, which is beyond the state of the art telemetry device which we have today. So, yes.
Do you use data compression at all?
That's the motivation. Yeah. If you do not do compression, that's the requirement. But if you do, then you can significantly reduce that requirement. So, that motivates us to do on-chip data compression, so that the requirement in terms of bandwidth and power is significantly reduced. And the second one is that we need to do online real-time analysis of the recorded data for recognizing significant patterns, and we will talk about that. You need to actually recognize the patterns for closed loop control. Now, let us look into the signal processing electronics. If you want to implement those two tasks, it turns out that conventional DSP or processors are either too power hungry or they are too big. For example, if you look into the latest processor from Intel, that is Atom, that is built with 45 nanometer technology, that is world's smallest transistor as of now. The size is not too bad, it is 26 millimeter square, although we need smaller one, but the operating power is in the range of watt, 1 to 4 watt, that is a lot. Standby power is not mentioned. There are different levels of standby mode of Atom processor, but it is still in the range of few milliwatt. The frequency of operation, of course, is very high. You do not need that high a frequency, but the power and size and standby power are definitely not suitable for implantable applications. If you look into the DSP from TI, the latest one has a size of 144 millimeter square. That is a lot. Operating power is 58 milliwatt. That is not too bad, although we need less than a milliwatt, as I have shown you. The standby power is 0.12 milliwatt, and the frequency is 108 megahertz, which means that if you want to process 100 channels, you cannot do that with this processor. And also the power budget is extremely high compared to our target. The area is also very high. So, it turns out that the typical DSP and processors which are designed for general purpose use are not good for implantable applications. So, what can you do? You need to develop custom hardware tailored to the signal processing application, and you need to do algorithm hardware co-design. For example, you need to develop algorithm which are amenable to hardware implementation. There are today many algorithms which are good for offline processing, where you have infinite computing power. You can have a server to process the neural data, but you cannot afford that inside the body, or you cannot afford that inside the implantable system. So, you need to develop algorithm which is suitable for hardware implementation. Also, we can develop architecture circuit co-design techniques. So, your circuit and architecture should not be decoupled, they should be developed together so that you can optimize the power and area. So, let us look into the system again. So, this is the system you are targeting. Now, the major tasks are denoising, spike sorting, which tries to identify the source of the spikes, identification of burst, and recognition of appropriate pattern. And these 4 steps are grouped as vocabulary based analysis, because that is an algorithm we are looking at. We are trying to find out distinct patterns of spikes and trying to group them together. So, this is called vocabulary based analysis. The basic idea is to find out the vocabulary of the nervous system, and if you can do that, then not only you can compress your data significantly, as we will show it shortly, but you can also identify behaviorally meaningful pattern from multi-channel neural recorded data. So, this is the idea of vocabulary based analysis, which is developed in our lab, and it is tested on pre-recorded data from the ganglia of sea slug. So, this is the overall flow. If you think about signal processing, in a typical neural interface system, we need to perform these steps. Now, this is a lot of computation. We cannot do it using a simple PIC or microcontroller. So, we need to come up with application specific hardware which can operate at a very low power and which requires very low die area, right. So, this is the application of the algorithm on several recorded data, and you can see that it can do almost perfect denoising and spike identification. In terms of compressing the data, if you do such an analysis, the compression can be significant, and of course, the compression depends on your level of alphabet symbols in the vocabulary. If your symbols are individual spikes, then your compression is varying from 24x, 3x to 24x. If you are looking into slightly higher level information or information at the burst level, then you can achieve significantly higher compression, that is from 66x to 446x. And if you look into burst level information where you do not store you basically store only spike intervals, basically you are missing some data in the burst level representation, then you can achieve further compression. So, it turns out that if you do compression, then you can achieve significant reduction in bandwidth requirement and also transmission power. As I mentioned, one objective of the vocabulary based analysis is to identify meaningful pattern from the neural signals, because if you want to do a closed loop neural control system, you need to identify the behaviors from recorded signal. Now, it can be done if you know the correlation of different channels, if you know the correlation of neural activity across different channels that corresponds to different muscular activity. If you have that a priori knowledge, you can look for such patterns across channel and you can find out behavior, and this is done on pre-recorded data from aplysia for different biting and swallowing patterns. As you can see here, there are different instances of biting and they have common feature. If you look into the difference between biting and swallowing, the difference are that activity on BN2, BN2 is particular nerve is delayed more in the case of swallowing, and it is reflected by the increased activity in nerve BN3. So, if you have this a priori information, then you can look for that information in the neural signals and relate it to meaningful behavior, and if you can do that, that will help you to achieve closed loop neural control. And with the kind of processing we are talking about, we can actually identify meaningful behaviors from neural patterns efficiently. So, that is about the algorithm. As I mentioned, this algorithm has to be amenable for hardware implementation, and the algorithm we have developed is amenable for hardware implementation. We have done some preliminary analysis. Now, let us see what kind of techniques we can implement, or what kind of techniques we can explore for implementing this particular algorithm. The question is that can we leverage the benefits of nano devices while addressing the challenges. Now, we know that the promises are in terms of density, low switching power and high performance, but definitely there are a lot of challenges. For example, leakage current, less robust switching, high defect rate and parameter variations, which corresponds to low yield. And for the emerging nanoscale devices like carbon nanotube, like nano wires, they may not be good for computation, they can be good for memory. So, can you somehow use memory for computation, right? So, these are the challenges. Now, let us look into several techniques. The first technique I will be looking into is a low power technique. Now, before that, let us look into the architecture. This is the architecture and several building blocks are inside there. If you look closely, you will see that there are two major components. If you look at high level, the components are in terms of logic and memory. So, you have to realize memory to store data and logic for computation, and these are the features. The features are, we need ultra low power, we need low size and lightweight. It has to be reconfigurable. Hardware reconfigurability is important to adapt to individual nervous system or to adapt to changing condition of the patient, and it has to be robust. The other features are biocompatibility and security. By the way, this is an emerging requirement, and I will talk about that shortly in the next slide. And the overall idea of the hardware implementation is to exploit the nature of signal processing to develop efficient hardware implementation paradigm. So, can we exploit the nature of the algorithm to implement efficient hardware? Now, that is the key question here. Now, let us expand on the security and privacy issue a little bit. It turns out that implantable systems are vulnerable to security issue. And what kind of security issue? Like eavesdropping. If we have a hard device and that is transmitting wireless signal, now somebody, an hacker, can eavesdrop, and somebody can also tamper the system. So, these are two major problems, security problems in implantable systems. So, along with low power and low area, it turns out that an emerging problem with implantable systems is security and privacy. And by the way, Dr. Wolf actually pointed this out, and then I found that in internet there are already some work going on to make the implantable systems more secure and more hacker proof. So, let us talk about low power design techniques which we have developed in our lab. Now, there are different techniques for reducing power. One technique is called supply gating, which basically adds a transistor in series with a logic gate to reduce the leakage current. And the idea is that if you add extra transistor which is turned off for saving power, the virtual ground voltage or the voltage at this node becomes slightly higher than 0, and that reverse biases this transistor, which effectively reduces the leakage exponentially. So, that is the idea. So, supply gating has been proven extremely effective for reducing leakage current, both for logic and memory, but they have not been used in the active mode of operation, which means they are used only in the standby mode when everything is turned off. So, if you want to use it in standby mode, you have to be careful, because in standby mode the outputs are floated. If you turn it off, if you add a gating transistor and you turn it off, the output becomes floated. So, it is a major challenge to use supply gating for reducing active leakage or the leakage in active mode. Okay? But it is an extremely effective technique. The leakage reduction is 5 to 20x. That is a huge reduction in leakage, but the problems are in terms of overhead and in terms of the fact that the output becomes floated. Now, we developed a technique called dynamic supply gating or DSG, which can reduce the leakage current and switching current in the ideal blocks of the circuit. So, this is an example. What we do, and this is a tree type circuit, it is a decoder. What we do, we can decompose the circuit into two blocks, and we can find out that only one block has active output. The other block, the output of the other block is not being used actively. So, what we can do? We can turn off parts of the circuit using particular value of the input. So, it is an input pattern dependent turning off, and you have to be careful to turn off, careful in selecting which block to turn off. For decoder it is easy, because you can take the signal from the pre-decoder and turn off the post decoder units. But for random logic you need to be clever, and it turns out that one can also apply similar technique to random logic by decomposing the random logic into independent blocks. There are techniques to do that. I will not go into details, but if you do it, then it turns out that not only leakage power, but also there is a significant reduction in in switching power, because you are effectively turning off this particular unit in terms of switching too. So, the overall improvement in power can range from 20% to 60 or 20% to 80%, and the improvement increases with scaling, and that is a nice feature, because if you scale, then you have higher improvement. Now, this is a simulation result for a set of circuits, logic circuits of different complexity, and we can see that the power saving can, on an average, can be about 45%, and this power includes both leakage and dynamic power. Another interesting design technique which we are looking at in the context of implantable system is that due to process variation, some blocks can fail, right? So, if you have a signal processing unit, some blocks, not all blocks can fail due to process variation. Now, can you limit or contain the failures to non-important blocks or non-significant blocks? So, that is the idea. Now, it turns out the typical signal processing application can be decomposed into significant components and non-significant components. Now, if you can make sure by a preferential design approach that all failures that happen in the circuit only happen in non-significant components, then you can ensure graceful degradation in quality. For example, if you are doing, let us say, discrete cosine transform, it turns out that for discrete cosine transform only 20% of the components are significant, 80% components are not significant. So, if you have failure in those 80%, the overall image quality will not be that bad, and I will show you shortly. So, that is the idea, and what we did, we tried to decompose the components into important or significant components and non-important or non-significant components, and then we try to design them differently. We try to make sure that the failures do not happen in important components by giving them more timing margin or delay margin, and we try to make sure that we actually save power and area in the non-significant components by designing them aggressively. So, that is called preferential design, because some part of the logic are overly optimized, but the others are not, and you can do it, apply it hierarchically. So, that means that for most significant bits which are more important in terms of overall quality of service, you are giving more delay margin, whereas for least significant bits you are giving less delay margin. So, that is a new paradigm of computing. It is clearly applicable to signal processing requirements or signal processing algorithms in implantable systems. And then on the individual blocks you can apply dynamic supply gating for power reduction. So, if you do that, then this is we applied the technique for DCT or discrete cosine transform, And if you do a one level preferential design, you have significant improvement in quality. So that means that here the failure happens in all components, significant or non-significant. Here the failures happen only in non-significant components, and here the hierarchical preferential design is applied, which means the failure happens only at the least significant bits of the non-significant components. So you still reduce some, you still have impact on the quality, but that's not too much. So that's the basic idea. Now, if you do design in such a manner, then one can also reduce power by scaling supply voltage, and again this is applied to DCT. It's not done by our group, it's done by another group, and they have shown that if you do design like this, then one can significantly reduce power. And as you can see here, if your supply voltage is 1 volt, then existing methodology work, but if you reduce the supply voltage, existing methodology do not work, but such a preferential design does work. So one can reduce power significantly by using such a preferential design at the cost of quality of service, or by trading off quality of service. So the final slide in terms of the design methodology is a methodology for reconfigurable computing. It turns out that for implantable systems, one needs to tune certain hardware, and that tuning is required to adapt to individual nervous system or to adapt to changing condition of the patient, and hardware reconfigurability is typically achieved by field programmable gate array. Unfortunately, field programmable gate array cost 10x more in power and area. That is a huge overhead to achieve programmability. Now, definitely for implantable system, a PGA is not good due to the power and area requirement. So we developed a methodology to implement reconfigurable computing, and this is called memory based computing. And in this computing, the idea is to use a huge memory array and compute the signal processing functions using lookup tables. So you have a 2-dimensional memory array, you store the functions in the form of lookup table in the memory array, and then use a central controller which is very small to read the lookup table in sequential and topological manner. So that's called memory based computing. We have introduced it and we have got several publications on that, and it turns out that such a memory based computing framework is reconfigurable, very low power, much low power compared to a PGA, and can also have less area, because if you have a high density memory array, then you can do resource usage much more efficiently. Another important feature for this approach is that since your basic computing element is memory, this is amenable to nanotechnology, because as you know, for non-silicon nanotechnology or non-silicon devices like carbon nanotubes, single electron transistors or quantum dots, they are not good for logic design, they are good for high density memory. So if your basic computing element is high density memory, this computing paradigm becomes very, very suitable for emerging devices. So this is some initial result. We can see that we have improvement in major parameters, delay, area and energy per vector for several combinational circuits. So with that, let me summarize. With the advances in nanoelectronics, implantable systems are poised to play major role in electronics industry. Okay, and that's a verdict, and I think that will be true. With increasing number of channels and higher temporal resolution of recording, it's very important to have onboard computation unit for compressing data and for analyzing patterns in real time. Nanotechnology definitely can have positive impact on the design of high density electrode array, and several researchers in this department have also proven that. It can also drive ultra low power and dense signal processing hardware design. We are looking into that, and if you really want to achieve it using nanoscale devices, you need to develop appropriate hardware and appropriate circuit and architecture design styles tailored to those particular signal processing algorithms. And that's it. Thank you.
Any questions, please? Questions, please?
I'm just curious, what is the range of sampling frequency required for these embedded law systems?
Yeah, the typical sampling frequency is 25 kilohertz, and one can go for higher sampling frequency, but for this particular experiment with C-slug, we have seen that 25 kilohertz can do that. But the problem is that you need to have hundreds or thousands of channels sampled at the same time and processed at the same time. So that is a major problem in terms of signal processing requirement. And you have to process them in real time. So major computation requirement.
Another question?
System.
Thanks.
Well, you talk about analog electronics, right? For biomedical applications, typically the signal bandwidth and the dynamic range may not be as stringent as other applications. So in those areas, we actually leverage from old technology, something on the order of a micron. Cost is low, design is cheap, and I'm not sure how we can benefit from nanoscale electronics when we're moving to analog electronics. And also when you talk about signal processing or microprocessor design, do you really need to use, for example, something on the order of 35, 45 nanometer technology for biomedical implants where those leakage issues become such critical, right? You may, for example, I don't do this, this is not my area. My guess is you may look at, for example, specific applications, right, requirements versus channel ones. You may get around with, for example, 180 nanometer or 90 nanometer, where the problem may not be as severe.
Yeah. Let me first question for analog electronics. Yes, you are right. I mean, you may not need to go to 45 nanometer, and if you go there, there will be several issues like robustness issue, right? So you have to be careful there. And as I mentioned, analog electronics do not scale as well as digital one. I do not know which technology would be good for analog electronics for implantable devices. Yeah. Steve can answer that question better. For for digital one, of course, I can definitely say that nanoscale devices have huge potential. The reason is that we tried to implement this particular algorithm with 180 nanometer, and the die area we are coming up with is huge. You cannot afford that.
How big is those dies?
I think it was like 22 millimeter. No, I'm sorry, 2 cross 2 for a very simplistic implementation. 2 millimeter cross 2 millimeter for a very simplistic implementation. And if you really want to afford to have higher channel counts, then the area goes up significantly. So in terms of area requirement, there's a huge benefit. In terms of switching power, there's a huge benefit, but definitely we have to take care of the leakage issue.
Yeah.
So I personally believe that it has a strong positive impact on implantable electronics in terms of signal processing.
Another question?
I have a couple of questions. One is in the vocabulary-based the neural interfaces. Do you find is there any problem with variations between organisms for those vocabulary?
Very good point. Yeah, the vocabulary-based analysis actually depends on supervised learning. So to start with, you have to learn what are the spike shapes for this particular organism or for this particular nerve cells. So once that learning is over, you have a built-in vocabulary, and then you can encode your recorded signal using that vocabulary.
Yes. And the other question is, vocabulary-based computing, you showed benefits for power and area, but I'm assuming that when you have that kind of architecture, your output will actually have some error, or it could have some error. Is that right?
No. It all depends, because if your memory is not erroneous, the output should not be erroneous.
But if you're constructing a lookup table, you could, in order to faithfully simulate some function, you might need enormous lookup table. Is that right?
Very good point. The lookup table size, there is a trade-off. If you increase the size of the lookup table, the number of cycles can reduce, but the memory requirement will go up. So we have a recent publication which shows that you can exponentially reduce the size of the memory by going to a different memory architecture that's called content addressable memory. Instead of addressing the lookup tables by address index, if you address by the value, you can actually reduce it significantly. So there are two optimization parameters here. One is the number of cycles, another is the memory requirements. And I mean, you cannot probably optimize both at the same time.
Another question? Just the last question. Would you comment about the battery requirements for these implant things? Because what kind of batteries you use? Are they essentially, fed sometimes from the body? I've read about that, or is it standard battery technology? Could it be passive? These kind of things.
Yeah, I mean, you can have again. We have not implemented these things, so
Okay.
we can have lithium-ion battery, which Steve has already a system which is based on lithium-ion battery. I think Darren is looking into recharging from outside, inductive recharging from outside. So that's the best, yeah.
You can get some very small batteries. There's one that we're using. It's 3 milliamp hours, lithium ion, and I can't remember the dimensions, but it's perhaps 10 millimeters long cylinder, and the cylinder is about 1 millimeter in diameter. So they're making some very tiny batteries for these implantable devices, but
How many hours?
3 milliamp hours at 3 volts, so we're talking about 10 milliwatt hours.
That's a lot.
These are not rechargeable, right?
That is
They're rechargeable
rechargeable.
also? How do you recharge though?
That's a challenge too that Darren could talk a lot
Yeah,
about. You have to blast away with an RF field and have a pickup coil to.
Okay, I guess if there's no other questions, thank you very much again.